Okay, biochem, here we go. Today is all about proteins and then their structures connecting to their functions. It's a pretty big quantitative day in terms of like how biochemists think and what biochemists do. And so these are our learning objectives. We're going to be focusing on globular proteins today, but some of these concepts will apply beyond just the globular proteins. We're going to talk about allosterics. We're going to spend a lot of time on this concept of KD. We're going to do some thermodynamics and some cooperativity. So let's talk about how I framed this as like a story. So this is a 3-part story about how a globular protein called serum albumin, and really it's, I guess I should say human serum albumin, which its abbreviation is HSA, human serum albumin, reversibly transports hydrophobic drug molecules through the body's bloodstream. So we're going to start with just the structure of serum albumin, then we'll do binding, and then allosterics and cooperativity. Okay, so what the heck is a globular protein? There's going to be 3 main kinds of proteins that we talk about in this class, and globular proteins are water-soluble proteins, so they're hydrophilic on the outside, and they have a hydrophobic core. And so if you look at this little diagram here, I've got an N to C backbone with all of the amino acids sticking out. The hydrophobics are in the purple and the hydrophilics are in green. And when this folds, all the purples go in the middle, all the hydrophobics go to the core. We call this the core, the inside. And the hydrophilics are on the outside. And this is driven by the hydrophobic effect because remember, everything in biochemistry is in water. And then this is sort of like a 3-dimensional structure of a globular protein where all the hydrophobic amino acids are buried on the inside, hiding away from water, and the hydrophilics are on the outside. And the protein that we're talking about today that's globular, so it has a hydrophobic core and is water-soluble, is called serum albumin, human serum albumin. And you may have heard of human serum albumin or the albums and serum albums, or they have they actually have a few functions. Let me introduce you to serum albumin. This is serum albumin. Its highest level of protein structure is tertiary, so that means it's a monomer, only one N to C termini. It's called the heart-shaped protein because it kind of looks like a heart. And it's usually always oriented so that you can see like the heart like face forward. It is the most abundant protein in your blood. I didn't leave myself enough room there. Sorry about that. Protein in the bloodstream. Okay. Its typical function, or its like canonical function, is to sponge up fatty acids. So fatty acids that are floating around in the bloodstream would probably clump together and cause like plaques and clog it up, and because they're so hydrophobic. And instead of clumping up and causing all sorts of like deleterious effects in your body, they actually bind to these little grooves on serum albumin. You probably can't see too many of them because this is a 3D structure and I'm trying to draw 2D on top of it, but the fatty acids will bind to serum albumin, and serum albumin sort of transports them around. So I don't know, think about it maybe like serum albumin's kind of like a taxi or a bus, and all the fatty acids get on board so they don't get stuck in the street, and they get transported to locations that need them. We're not going to focus on albumin's function as a fatty acid carrier. We're actually going to look at it in the context of what's the field of what's called pharmacokinetics. And that's how do we get drug molecules? How do we get drug molecules that are relatively hydrophobic to their destination location? So a lot of the drugs that you ingest or eat, and I'm going to use ibuprofen as our main example of this. So ibuprofen is one of your NSAIDs. I'll just draw the structure really quick. I'll draw it at pH 7. Okay, ibuprofen is relatively hydrophobic. Its amount of CHCCs in comparison to this 1-carboxylic acid is just more hydrophobic content than the other drugs. And so you take a hydrophobic drug and, you know, maybe a feature of it is it's able to cross through the plasma membranes of the intestinal mucosa or the gastrointestinal tract, and then it gets in the blood. And what do hydrophobic things do in the bloodstream? Well, they clump up and they cause problems. If it remains unbound and sort of clumpy, it can basically just get excreted out. So sometimes people are like, oh, those vitamins, you're just peeing them out. Okay, that's sort of the concept here is like, if it gets into the bloodstream, it will likely just get eliminated. It could also be inactivated. But if it gets sponged up by serum albumin or another type of globular protein that carries drugs, then it has the possibility of actually getting to its receptor. So that's kind of what we're going to talk about today, is the binding of drug molecules to serum albumin and how they get to their receptors. But of course, we're going to do it biochemically, so that means we're probably going to talk about numbers. And this process, before I move forward, this process has to be reversible, meaning that when said drug molecule or when said, let's say, ibuprofen attaches to serum albumin, when it gets to its location, that ibuprofen has to leave serum albumin and it still has to be ibuprofen after it's left. Serum albumin cannot chemically alter it because then it's a different drug and it could be inactivated. So again, serum albumin in my mind is sort of like a taxi or a bus that loads up hydrophobic things and takes them to their destination and opens the door and they exit back off. And it's the same thing that entered, it's the same molecule that entered the bus as it is leaving the bus. Okay, this is just another figure that I thought was really nice about the serum albumin so that you can see a little bit more about its structure. Again, it is a globular protein, and that's important because it's soluble in the blood, which is mostly water, so it needs to be soluble in a watery area, so that means it's globular. It's pretty much all alpha helical. I don't see any beta strands or beta sheets in there. But these figures over here just show serum albumin bound to different things. So when bound to fatty acids, it can bind a whole bunch of fatty acids. It can bind this hydrophobic thyroid molecule. It can bind some ions. And then it can bind drugs like diazepam. All different bindings, different binding sites. And we'll talk about that, what that means and why that's important. Okay, so let's start with this idea of the fact that the binding has to be reversible. So I'm going to do a lot of drawing and a lot of like cartoon drawing. Okay, so as like a cartoon example, I'm going to make my serum albumin the heart shape. And let's say there's an important over here, NH3 side chain sticking out with a positive charge. Let's say it's a lysine. Okay. Let's say it's a lysine. And this is a really important way for my ibuprofen like this. It would be like connected really well. But this is a really important way for the ibuprofen to sort of like stick to the serum albumin, okay? And then in order for it to be reversible, that means that all the connections that the serum albumin and the ibuprofen make together must be reversible. So they have to be reversible, meaning they have to be non-covalent. They can't stick together so well that the process of the two never get unbound. Ibuprofen has to leave to be able to get to its molecular target to reduce pain and inflammation. Okay, so the way that drug molecules or small molecules or anything really binds to a protein is through non-covalent interactions, because they're weak enough to be broken easily so that the two can associate, dissociate, associate, dissociate. Okay, so in sort of more broad terms, in this case, ibuprofen is called a ligand. Ligand is the thing binding to the protein. And here, my pink one is the albumin, or in more broad terms, a receptor protein. Okay, and then I have that is in equilibrium with my ligand as separate, or I'm gonna put a plus sign. Actually, I probably could do that in a different color. My ligand is separate from my receptor. Okay, so I've got like a cartoon way and then like a words way of describing the same thing. And then we sort of take this down even further into just abbreviations of letters. So on my left-hand side right here, I have my ligand, which is L, and my receptor, I'll just do R, so we would call it LR, although more frequently you would see, why does that not want to erase? Bigger? Okay, fine. You would see, it would be like P to L, which this indicates the protein. And this indicates the ligand. And I could put parentheses and a 1 here, but that's sort of mute. But that means that when the two letters are together, the two pieces are connected. They're connected non-covalently. And those are in equilibrium with the ligand being free of the protein receptor. So L plus P. So L, or ibuprofen, not bound to the serum albumin. Okay, so that's my way of like trying to connect some of the words and the nomenclature with a cartoon diagram here. And notice we have a double-headed arrow, meaning that this could go in either direction. That's the reversibility. The other thing that I'm hoping that you noticed here is that no reaction has occurred. What went into the reaction, the ligand, is the same thing that's coming out of the reaction. Ibuprofen goes in, ibuprofen comes out. Protein goes in, protein comes out, and vice versa. Okay, so reversibility has to do with the fact that when the two are connected, it's non-covalently, and that this could go back and forth and back and forth and back and forth. Now, that's sort of like the conceptual understanding of what we call protein binding, but because it's biochemistry, we like to do a quantitative way of being able to figure out like the degree of binding, like how good is this ibuprofen at binding to serotonin. And so when we add a quantitative or numerical value to this, we call that value KD. It's either K little d, sometimes you'll also see it K big D, and this is I guess I can move it here. This is the dissociation constant. Okay, and it's a measure of how well the ligand binds to the protein or the receptor, or the protein receptor. Okay, we sometimes also call this affinity, the binding affinity. Okay, numerically, KD equals the concentration of the ligand when 50% of the protein is bound to ligand. Okay, that's what it means. This is the quantitative definition, and this is what that means. Like when you get the quantitative number, this is the interpretation of that number is how well the ligand binds to the receptor. Okay, so now we're going to do some examples. Okay, so the simplest of cases here is to find KD from a graph. And the y-axis is called R, sometimes it's also called theta, and it goes from 0 to 1, and this is the percent bound of protein to ligand, okay? And the x-axis is the concentration of the ligand, usually in molarity, actually more usually in like nanomolar or micromolar. And the graph, in the most simplest of cases, looks like this shape, which the shape is hyperbolic. Okay. So let's say that in our case, we are trying to measure the affinity of ibuprofen for serum albumin. Oh, I'm gonna make my graph just a little bit more specific then. And that means that this will be ibuprofen. That's my ligand, and I'll measure it in nanomolar. And so here's how you find KD from this. You go to 50% binding, or 0.5. This is 50% binding. Drag a line over to the curve and drop it all the way down to the x-axis. And just, I don't know, for the sake of simplicity, we're going to say that this is 2 nanomolar. And so that means the KD here equals 2 nanomolar. That would be the binding affinity of, for when our serum albumin is bound, I'll just make ibuprofen blue. Color am I using? It's hard to see the difference between my pink and my purple. Okay, so that means this value right here, KD, means that it would take 2 nanomolar concentration of ibuprofen to get half of the serum albumins docked with ibuprofen. So if I only had 2 serum albumins, then it would take a 2 nanomolar concentration of ibuprofen to get half of them, or one of the 2 bound to protein. And if you wanted more binding, more than 50% of the serum albumin bound to ibuprofen, you'd need to increase the concentration. So let's say you increase the dose to 4 nanomolar ibuprofen, and that's 4. Then I would have, I don't know, let's approximate that to like 80% of them bound. And we'll kind of get into like, what does that mean later? Another useful thing about the KD is it's a way to compare the affinity of different drugs or different ligands for the same protein. Okay, so now let's say that we have 2 NSAIDs, and all of the NSAIDs are relatively hydrophobic, so they do need to bind to serum albumin in order to get transported. And one of them will be acetaminophen, and then we'll compare to the blue one, ibuprofen. Okay. So I find that, experimentally, I can measure the affinity of acetaminophen with serum albumin. And let's say I get a graph That's a little bit like this. Again, this is R 0 to 1. And then I also have my ibuprofen 0 to 1. Looks like this. And I had already decided that my KD from this one is 2 nanomolar. And if I look at my acetaminophen, my KD over here is 5 nanomolar. Now already I know that a larger KD is weaker binding, and we're going to mathematically prove that. Okay, so I can use KD as like an apples to apples comparison, and the bigger the KD, the weaker the binding. And what that means is the acetaminophen should have a less negative delta G, right? Because if the binding is really the association between the two and it's non-covalent, that gets us into thermodynamics. So let's take a look at quantitatively how does this weaker binding, or the KD, link back into delta G. All right. Oops. Okay, so just as sort of like a reminder, so better binding equals either more or stronger, or both, non-covalent interactions, which should be a smaller KD. Smaller KD means better binding, and that should also mean a more negative delta G. All right, so if you may remember an equation, or you may not, from Gen Chem, that was delta G is negative RT ln Ka, or the association constant. Well, it turns out that Ka is simply the invert of Kd. So I can rewrite this equation to be delta G is positive RT ln Kd. And for our case, R is going to be 8.315 joules mole Kelvin. We'll do 298 for Kelvin. All right, so let's see. We had our two cases. We had acetaminophen plus human serum albumin, and that KD, just from the graph from before, was about 5 nanomolar. And then we had ibuprofen plus human serum albumin, and that KD, again from before, was about 2. Okay, let's go ahead and put this into the equation. So R delta G equals R, which is 8.315 joules mole Kelvin, 298 Kelvin, times the natural log. Now, if you just put 5 in here, it's not going to work. You need to convert to molar for both of these. So 5 times 10 to the minus 9 molar. And then this one would be delta G, joules mole Kelvin, 298 Kelvin, times the natural log of 2 times 10 to the minus 9 molar. Another thing that you'll notice is that this Kelvin and this Kelvin will cancel out in both. So your final units on delta G should be joules per mole. Okay, so let's do that calculation. Okay, so I got for the acetaminophen with the higher KD value, I got negative 47362, so 47,362 joules per mole, again negative. And then for the smaller one, I got negative 49632 joules per mole, also negative. Okay, so this all totally checks out because remember, the bigger the KD, let's do the other way. The smaller the KD, that's in this case 2 nanomolar compared to 5 nanomolar, the better the binding, and the more negative the delta G. And this one is a more negative delta G than this one. If when you're doing these calculations you don't get a negative delta G at all, you've done something wrong. Like the interaction, if in order for it to occur, they must be interacting, forming non-covalent interactions, and that will have to give you a negative delta G. So that all checks out. So what does that tell me? That tells me that basically if you were to, and don't do this, but let's say you were to take both acetaminophen and ibuprofen at the same time. Don't do this. Like if you take them both. Again, don't do this. And assuming they bind to the same spot on human serum albumin. Okay, so that means my green acetaminophen and my blue ibuprofen, they're both going and competing for that same location. What that means is that given a solution of all of these things, you'll have more, you'll have more ibuprofen bound to serum albumin than you would to acetaminophen because they're in competition, and ibuprofen binds better, so more of it will be bound to serum albumin. So one, it really makes no sense to take acetaminophen and ibuprofen at the same time. They're competitors of one another. And two, there's some other like toxic side effects to it as well. But just in terms of like biochemically and the way that things break down, ibuprofen would outcompete acetaminophen for that spot simply because it binds better. It's more spontaneous interaction with human serum albumin. Another important connection that we can make with this concept of binding and the quantitative value of binding. So if we go back to our hyperbolic graph, where this is ibuprofen binding to serum albumin, so R 0 to 1 amount bound, okay? At this sort of higher concentration region here of ibuprofen, okay, you would have, if I go like in the middle here, all the way up and all the way over, at this higher concentration of ibuprofen, you have almost all of it, all the serum albumin's bound to ibuprofen. Okay, so that means that up here, it's like almost, wow, click on the things that you want. Like almost 100% of HSA is bound to ibuprofen. I'll just abbreviate IB for ibuprofen, okay? Where is this happening physiologically? So you take ibuprofen, it goes into your gastrointestinal tract, it will start to cross over into the bloodstream. I wonder if I can draw a very quick gastrointestinal tract. Okay, so there'll be like my stomach is here, and then my duodenum is here. You've taken ibuprofen. It's coming into, the pill's coming in, it's getting split open, so you've got a bunch of ibuprofen here. Some of it moves into the duodenum. It's going to move across the gastrointestinal lining, right? And the how much of it, or how much of it's moving over is dependent on the charge in the two different places that we kind of covered before. But right where the bloodstream is sort of like moving past the gastrointestinal tract, that's where your highest concentration of ibuprofen is. Okay, so as human serum albumin is floating by, you are in this high concentration of ibuprofen, and so it'll sort of like sponge them up. So all of these get their ibuprofen, right? And then the blood sort of swooshes by and moves to a region far away. Let's say, ibuprofen, you took it because you bumped your hand, you got your hand stuck in between a door or something and it hurts really bad. That like blood moves far away to sort of where your hand is, and it's all loaded. These HSAs are loaded up with ibuprofen. Now you're in a region of whoa, crap, that's not what I thought I was doing. Oh no, how do I get it back? I don't get it back. That's unfortunate. Okay, so now you're in a region, I thought I clicked the highlighter. I did not. So now you're in a region down here with low ibuprofen. And when you've got low ibuprofen, much less is bound to human serum albumin. So now it's dissociating from or leaving from the HSA. So maybe this region right here represents like the blood in your hand or something. And this region right here represents the blood near gastrointestinal tract, Okay. So the hyperbolic curve can kind of tell you a little bit about the physiology of it. So again, if I were to sort of diagram this kind of in another different way, I will on purpose erase this. Underneath of this curve, I'll just do this one. Underneath, so over here at high concentrations of ibuprofen, my HSA is bound to ibuprofen. The two are together. And then as you move away, as that bloodstream moves away from the gastrointestinal tract, you'll have much less will be bound. So I'll have a lot of HSA, which is free from ibuprofen. And again, this is important because this ibuprofen needs to leave to go to its target, which is cyclooxygenase type 2, right? Because the idea is reversible binding back and forth and back and forth and back and forth. If you've maybe another way, maybe you're seeing this, maybe you're not seeing this, is if you remember Le Chatelier's principle. I don't think I spelled that right. But if you have, if you increase the concentration of ibuprofen, which would represent this region right here, then you shift the equilibrium to favor the bound amount or the bound state. And if you have a region where your low concentration of ibuprofen, that would be like this region right here, it shifts the equilibrium in this direction to be unbound, and then ibuprofen can reach its target. Cool, huh? So that's binding with thermodynamics, with non-covalent interactions, with equilibrium, and some numbers, and all the things, because we like to layer on all of our concepts in biochemistry. Okay, so this brings us to the very final part, and that is about allosterics and cooperative binding. So first I'm just going to define these for you. Allo means other, and sterics means shape. Okay? And cooperative binding refers to what happens when you have multiple binding sites. And usually allosterics go with cooperative binding. And there's 3 flavors of cooperative binding. There's positive cooperativity, where binding of first molecule increases the affinity for the second or so and such second, third, fourth molecule. Okay, and then there's negative cooperativity when the binding of the first molecule decreases the affinity for others. Okay, so again, in cooperativity, you have to have multiple binding sites. So I'm going to go back to our case of human serum albumin. Human serum albumin has a lot of binding sites on it, okay? And in this case, you're going to imagine that you've taken two drugs that don't compete for the same site. So ibuprofen here can bind to this site, and then diazepam, let's say it binds over here just to a second binding site. Again, working with non-covalent interactions, you can measure the KDs of them. And maybe you are taking these at the same time. I believe diazepam is like an anti-anxiety, so maybe that's sort of like a regular medication, and then you have a headache and you take ibuprofen at the same time, right? So you're taking two drugs at the same time. Both are relatively hydrophobic. They will cross the gastrointestinal tract, need to be sponged up by human serum albumin in order to reach their target. Now, the question is, if human serum albumin can bind to both of these, how does it do it, and is the binding cooperative or not? And so I'm going to sort of talk about, I said that there were three cases. There's the two main cases. I'm going to talk about each of these, but the third case is just not cooperative. Okay, so let's say the first case will do positive cooperativity. So that means in the instance that ibuprofen binds first with its particular KD, it can cause a change in shape that allows for this diazepam to bind better. Okay, so ibuprofen binds first, causes change in shape so that diazepam, I'm just going to go DZ, binds better when it comes in second. So that means that they are cooperating. They are working together. The first one binds and it helps the second one bind better, and both are bound at some point at the same time. Okay, in another case for negative cooperativity, let's say that ibuprofen comes in and binds first and causes a change in shape I'll just sort of like balloon this out, causes a change in shape so that the diazepam just cannot reach the non-covalent interactions, cannot reach the amino acids that it was interacting with. That means that the diazepam has a decreased affinity. It doesn't mean it's not going to bind to any of the HSAs, but it's not going to be able to bind as well to the ones that already have ibuprofen on them. And so allosterics and cooperativity, those tend to go together. And a reason for measuring this again is in this pharmacokinetics world, a lot of times drugs are taken, multiple drugs are taken at the same time. And you need to be able to know, like, can human serum albumin sponge up both of them? Actually, will it help if they're positive cooperativity? I guess I should do the third case, which is no cooperativity. So no cooperativity would be, so let's say ibuprofen binds first and diazepam, but no change in shape, and diazepam binds second, and they don't affect each other. Or diazepam binds first, and then ibuprofen binds second. It doesn't matter the order of operations. They're not cooperative. The binding of one does not influence or sort of help the binding of a second one. So I think that is, oh wait, no, one little last thing, just as like a note about KD. The magnitude of KD does matter, and stronger binding, stronger KD is sort of in this range right here, and weaker binding is here. Here's some examples of humans, protein receptors, and then their ligands and their KDs. So you can see, I don't know why I like scribbled over that whole thing. That just seems absolutely not helpful. The most, whoa, that's not a highlighter. Focus. Okay. The one that has the smallest KD here, this 1 times 10 to the minus 15, is the binding affinity between avidin protein and biotin. In this case, the one with the weakest is calcium binding to calmodulin. So this is just to kind of give you a sort of scale in your mind about like what high affinity, lower KDs mean versus bigger KDs and weak affinity, and some different types of things to do that. Okay, we're going to practice a lot with this, and I will see you in class. Bye!